In one of our last videos, we discussed the many layers of the Earth's interior. In response, it is easy to ask how science has come to learn this, so let's explore it. First, an earthquake must happen. Earthquakes occur after the pressure that builds between two tectonic plate boundaries that are sliding past each other is released suddenly and all at once. This release of pressure can move millions and probably billions of tons of Earth for all I know. They move in two different types of waves, body waves and surface waves. The body waves are the ones that can go down deep into the Earth interior, whereas surface waves stay along the outer crust of the Earth. The first type of body wave is a primary wave, and it moves in a push-pull wave and can travel through solid, liquid, and gas. The slower, secondary waves are different because they move side to side, rather than pushing and pulling. The damage from earthquakes is the result of those surface waves traveling along the upper crust. Here's the thing about all these waves. The way they behave entirely depends on what they are traveling through, whether they are traveling through liquid matter or solid matter. To provide a better example, imagine swimming in a pool when someone on the other end jumps in. You probably won't feel those waves until some time. But if you held a metal pole while someone hits the other end of it with a hammer, well, there's no mistaking what would happen then.
Bad vibrations?
Because the state of the matter controls the behavior of these waves, when geologists track the wave movement and see them getting knocked about, the conclusion is that the Earth interior must contain a variety of liquid and solid layers. We can use mathematics and finely calibrated machinery that would take a physics degree to wrap your head around to understand, but to measure at which depths the changes from solid to liquid to solid again occur within the Earth. We are going to focus on what's going on in the solid upper crust layer though, because that layer has been changing a lot through time. The two types of crust are continental crust and ocean crust. The ocean crust is colder and more dense because the weight of the ocean packs it down to a thinner layer. The continental crust is thicker and less dense because the atmosphere is way lighter than the oceans. Notice that the boundaries of the continents don't always match with the boundaries of the tectonic plates. Our book describes a cool experiment that I'm quite a fan of. Blocks of wood are floating in the water. The wood is like the continental crust and the water is like the liquid mantle. If we stack the blocks of wood on top of each other, then the lower blocks would be pushed deeper into the water under the weight of the blocks on top. Likewise, if we removed the top blocks, like the water streams that carve sediments from the top of the mountains, the lower blocks would spring back up towards the water surface. This explains how something like an ancient magma chamber can be deep underground at one point in time, and now is exposed at the top of a mountain. The geologists call this isostasy. There's an interesting historical story related to the mapping of the ocean floor, which I'd encourage you to read, but don't stress too much about it. Additionally, there is a historical account of the theory of plate tectonics, which is interesting, but I'd rather stick to the practical applications of the plate tectonics theory for historical geology. The clues for the plate tectonics theory vary from the jigsaw puzzle fit of the continents, the distribution of fossils across geography, and even the orientation of metallic crystals. Because just like the Earth's magnetic field pulls the compass needle north, they pull on metallic minerals when they are in a liquid state. When they cool, that orientation is frozen in the current state of the rock that we see today. This observable condition opens the door for studying the history of this magnetic field and how it has changed through time as well. Fun fact, it's been reversing back and forth a lot. Now, the book also talks a lot about the different kind of plate boundaries, so I'm going to try to break it down. Convergence is where plates are being pushed together. If a piece of dense ocean crust is pushing on continental crust, then the dense ocean crust slips underneath the continent, just like the dense oil sinks below water. If two continental crust pieces get pushed together, they force each other up, which is how the Himalayan mountains formed. The opposite, ocean crust pushing on ocean crust, results in deep ocean trenches. There are two other boundary types. Divergent boundaries are when crust pieces are moving away from each other, which is occurring at the Atlantic Ocean about halfway between North America and Europe. Transform plate boundaries are where they're sliding past each other, which causes the earthquakes that were discussed earlier. For an overview of the mechanisms that drive the movement of these plates, I'm assigning some additional videos in your Lesson 7 module. These sources have some great animations that can probably do a better job at explaining it than I can, in words. You know, I just got through the rest of the chapter, and I couldn't really find anything that is crucial to our understanding of historical geology at this level, so we will just call it here. The topics of folds, faults, strikes, and dips are part of a discipline called structural geology, and I'll save those topics for our live discussions. So thanks for listening.